A stationary ball is hanging from a light string. A pellet from a rifle is traveling horizontally and becomes embedded in the ball. The velocity of the pellet when it strikes the ball is 160 meters per second. This is the diagram. This is the path of pellet, and this is the ball. The following data are given. Mass of the ball 250 grams, mass of the pellet 2 grams. Calculate the speed of the ball and the pellet immediately after the impact. Okay. So mass of the ball, if we convert into kilograms, it is 0.25 kilograms. And mass of pellet, if we convert into kilogram, it is 0.02 kilogram. I will call it as MB, and this one MP. Wait. Okay. And after that, according to the information that velocity of ball is 0 and the velocity of pellet is 160 meter per second. Calculate the speed. According to the principles of conservatory of momentum, that mb times vb plus mp times vp, this before collision and after collision, mb plus mp times v. V is velocity after collision. This is v. Or we can arrange this formula if v is the subject. Becomes mb vb plus mp vp over mb plus mp. mb times vb is mb times vb, I mean, is this one, 0.25 times 0, and mp times vp, 0.002 times 160 over mb plus mp, 0.25 plus 0.002. And it is, the velocity becomes, this is 0, and if you calculate this, 0.252 over 0. This is 0.25, sorry, 0.252, this one. 0.252, and this is 0.32. And if you calculate this, it becomes 1.27 meters per second, at least. Suggest why combined kinetic energy of the ball and the pellet after the impact is less than the initial kinetic energy of the pellet. I have provided my uh, explanation about this, and this one the explanation. After the pellet embeds into the ball, both the ball and the pellet move together as a single object. The system's total mechanical energy or kinetic energy decreases because the combined system, ball and pellet, it will move with a lower velocity than the pellet original speed, since the mass of the ball is much greater than the mass of pellet. This results in a lower final kinetic energy compared to the initial kinetic energy of the pellet. I think clear. Next. The ball with the embedded pellet rises to a maximum vertical height. Draw and label the free body diagram for the ball at height. So the directions are uh, the tension is this one with two upwards. The arrows, okay, this is tension and weight due to gravitational force to downwards. Okay, so tension is acting upwards along the string, and then weight is acting downward due to gravitational force. Determine 8. Just now, we already calculate about the velocity the velocity after collision, and the velocity after collision is 1.27 meter per second or 1.3 meter per second, rounded to 1.3. By conservation energy, we can calculate through this formula that half v squared equal g times h. If h the subject, this formula becomes v squared over 2 times g, or 1.27 squared over 2 times 9.8. And the result is 0.0822 meters, or 8.2 times 10 power minus 2 meters. Number 2, a student throws a ball towards a wall. The ball is released from a point 1.8 meters above the ground and 8 meters from the wall. The initial velocity of the ball makes an angle of 48 degrees with the horizontal. Air resistance is negligible. The diagram shows the initial path of the ball. P is a point on the path. This is P. Draw on the diagram an arrow to show first the velocity of the ball at P. Label this arrow V. Okay. The directions of velocity is like this. A straight line from point P towards there to upwards. This is V. Part 2, the accelerations of the ball at P, label this arrow A. Acceleration, uh, the acceleration direction to downwards because of gravitational force. So like this, to downwards. Okay, due to gravitational force. Next. The ball takes 1.3 seconds to reach the wall. Show that the initial speed of the ball is about 9 meters per second. Uh, on this on this problem, the horizontally motion gives us a formula that the initial velocity equal distance over cosine theta times t. Okay. According to uh, this diagram, that distance is 8 meters, and then theta is 48, and time is 1.3. This one. So we can calculate the initial velocity. Initial speed is 8.0 over cosine 48 times 1.3. And the result is 9.2 meter per second. Next. Determine the height above the ground at which the ball hits the wall. Okay. Initial velocity is initial vertically of velocity, I mean, or initial vertically speed. Uh, I give name V O Y because it's happening on y-axis. The formula is initial velocity times sine theta. Okay. Initial velocity is 9.2. Recently, we calculate it, and theta is 48. And if you calculate this, the result is wait, 6.83 6.83 meter per second, or rounded to 6.8 meter per second. Okay, the vertical motion on this case is described by the equation like this. The equation is H equal initial H plus v initial velocity on y-axis, okay, or the horizontally initial velocity, and vertically initial velocity. If horizontal initial velocity is v no v or v0x minus half gt. Okay, minus half gt squared. So substitute all information that the initial height is 1.8 plus the vertically speed is on y-axis is this one 6.83 times t. This is times t actually here. Okay, times t is 1.3 minus half times 9.8, 1.3 squared. And if you calculate this, the result is 2.388 rounded to 2.4 meters. Number 3, A fixed quantity of 4.5 times 10 power minus 3 mole of air is compressed at a constant temperature. The graph shows the variations of pressure P with volume V of the air. This is the graph. Next. Suggest whether the air behaves as an ideal gas during this change. I have provided my explanation about this for an ideal gas undergoing an isothermal or constant temperature process. The pressure and volume are related according to the formula by Boyle's law. Okay, the formula is one PV equal 12. Okay, this means the product of pressure and volume remains constant at constant temperature. I'm gonna show you why this 12 because look, the relationship is 4 on this coordinate point. 4 times 3 is 12. 12, this coordinate point. 3 times 4 is 12. As well, this coordinate point. 2 times 6 is 12. And then this coordinate point. 1 times 12 is 12. So that's why P, the constant number is 12. Calculate the temperature of the air. We are going to using this formula that Pv equal nRT, which are P for pressure of gas and V volume of gas, N is number of mole of gas, R is an ideal gas constant. Okay, R is 8.31 joules. Okay. So R is the ideal gas constant, while T is temperature. So we're going to calculate the temperature. So if temperature, the subject, this formula becomes PV over N times R. Okay, PV is 12 according to the number A, number 3A. So it means 12 divided 12 divided by n. N is n is 4.5 times 10 power minus 3 mole. According to this information, I'm going to show you this one. This is n. Okay, so is 4.5 times 3 times 10 power 3 times 8.31. And the result is 320.7, rounded to 321 Kelvin. The unit is Kelvin. Outline how kinetic theory of gases relates observable properties of gas to the motions of the molecules. I have provided as well my explanation about this part. The pressure is caused by the frequency collisions of gas molecules with the walls of their container. According to the kinetic theory, each molecule moves in random directions with varying speeds. When a molecule collides with the wall, it exerts a force and cumulative effect of many such collisions results in the observable pressure. The pressure is proportional to the number of molecules and their average kinetic energy. That's my explanation. Number four, a solid block of glass is covered with water. The diagram shows the path of a monochromatic light ray entering the water from the glass block. So this is the diagram, the incidence angle in glass is 55, and this is the refraction angle in water 71. The speed of light in the glass is 2.0 times 10 power 8 meter per second. Calculate the speed of light in water. State the answer to an appropriate number of significant figures. Okay, so this is theta 1, the first angle, and this is the theta 2, the second angle, theta 1 in glass, while theta 2 in water medium. Okay, so and V1, the velocity or the speed like in glass is this one. This is V1 or the speed light in the glass. We're going to calculate speed light in the water. This is for me V2, like this, the speed of light in water. According to Snell's law that V2, we can determine V2, or I would like to writing the main formula. The main formula is sine theta 1 over sine theta 2 equal V1 over V2. If V2 the subject, we can arrange this formula becomes sine theta 2 over sine theta 1 times V1. Now, if we substitute this information into this formula, it's going to be sine 71 over sine 55 times this number, 2.0 times 10 power 8. And the result is 2.292 times 10 power 8. And we have to writing in significant figures, it means 2.3 meters per second. Next question. Explain the change in the wavelength of the light at glass water boundary. I have provided my explanation about this. In the glass, the light travels faster and has a longer wavelength. According to the formula is lambda equals C over F. According to this formula, that lambda is wavelength, C is speed of light, and F is the frequency. When the light speed increases, when C increases and the frequency not change and F not change, the implication wavelength will be increased. I think clear this part. Next. The light ray is partly reflected from the glass water boundary. Draw on the diagram the path of the reflected ray. So the reflected ray towards to downwards on the glass medium with angle 55. 2. Identify the directions of polarizations of the reflected ray. I have provided my explanation about this. The polarization directions of the reflected ray is parallel to the boundary or parallel to surface line, the horizontal line. The water is removed and replaced with air. The refractive index of air is 1.0. This is N air. The directions of the incident light ray in the glass is unchanged. Direction unchanged. Determine whether light emerge from the glass block into the air. Right. So if this is uh, n n of n of air, so I will begin from identification that refractive index of water and 2 is 1.33. And then theta 1 is 55, theta 2 is 71. According to the Snell's law that we can determine N1. N1 is refractive index of glass, and 1 is N2 sine theta 2 over sine theta 1. And the result is 1. If we substitute 1.33 sine 71 over sine 55. Okay. And 1. So N1, if we calculate, the result is 1.52. This is the refractive index of glass, right? Now, if N air, the refractive index of air is 1.0 according to this information, and N glass is this one, this is N glass. So according to Snell's law, we can arrange the formula that sine theta glass over sine theta air equal no, theta equal n, okay, n glass or refractive index glass over refractive index air. We are going to find sine theta air, or sine theta air is the subject. We can arrange this formula becomes sine theta air equal n a over n g times sine theta g. And we can calculate sine theta air equal and A is 1.0 over 1.52 sine 55. Okay. And then the result is, if you calculate, the result is 0.52. 3, 8, 9, so on. And theta, it means theta air, according to this information, that theta air equal 42 degrees. I have calculated on my calculator. 42 is less than 90. Okay, if less than 90, it means the conclusion for this question is, if I would like to writing here, the conclusion is if sine, if sine theta air less than sine 90 or less than 1, so the light can emerge. Can emerge from glass block into the air. Number 5, a 50 ohm resistor is connected to a cell of electromotive force 3 volts. The voltmeter and the ammeter in the circuit are ideal. This is the diagram of a circuit voltmeter, and this is uh, the ammeter. This is the resistor. The current in the ammeter is 59 milliamps. Calculate the internal resistance of the cell. Okay, so I would like to identify that phi is the total voltage. Okay, total voltage, or the total uh, the total voltage of this circuit. Okay, or the electromotive force. I mean, this one, the total voltage or the electromotive force, and this is 3.00 volts according to this number. And currents, or I, is the current of this circuit, and this is according to this information that 59.0 milliamps. It means if we convert into amps, becomes 0.059 amps. So I would like to using this number. Okay, and next is total resistance, R. After that, the next step, we are going to we can calculate this resistance through this formula, that R equal, that is better if using this EMF over I is 3.00 over 0.059, and the result is 50.85 ohms. And if there is another resistance, I would like to writing R like this, the external resistance, and according to information that the external resistance is 50 ohms. Now the total resistance, of this space, the total resistance is external resistance plus internal resistance. This is the internal resistance. Okay. So it means internal resistance equal total resistance minus external resistance, or 50.85 minus 50.0. And this is 0.85 ohms. So internal resistance is this one, 0.58. Next, the circuit is changed by connecting another resistor in parallel. Okay, so attach another resistor, this one, and attach by parallel circuit, parallel to this resistor, to the 50 ohms resistor. Explain the effect of this change on the effect of this resistor to the reading of the ammeter, the implications of this resistor to the ammeter. I have provided my explanation, my opinion. One, that when another resistor R, this resistor, the additional resistor connected in parallel with the 50 ohms resistor, supposed to be this 50 ohm resistor, the total resistance of the circuit will decrease. Why decrease? Because this circuit add one more resistor, this resistor. This is because the total resistance of two resistors in parallel is always less than the resistance of either resistor individually. According to Ohm's law, if the total resistance decreases, the current through the circuit will be increased, assuming the electromotive force of the cell remains constant. Since the ammeter measures the total current in the circuit, the reading on the ammeter will increase after adding the parallel resistor. As the total current increase due to the reduced overall resistance. I think this is clear. Yeah, because based on the formula that current equal EMF over external resistance plus internal resistance. If resistance decrease, okay, whether external resistance or internal resistance, the implication for the ammeter, the current the current or the ammeter will be increased. The measuring of ammeter will be increased. Right. Next. So what are the implications for the reading of the voltmeter? Just now, when we add one more resistor here, this is the implications for the reading of the ammeter, and then next the implication, the reading of voltmeter. The reading of voltmeter, I have provided my opinion as well. The The voltmeter is connected across the external resistor, in this case, across the parallel combinations of the 50 for the 50 ohms. So this is 50 ohms resistor, and the second resistor is R. Since the resistors are in parallel, the voltage across them, which is what the voltmeter measures, the voltage across them will remain the same regardless of the change in total current or resistance. The reading on the voltmeter will not change, okay, when the second resistor is added in parallel to the 50 ohms, suppose it is 50 ohms resistor. It will still show the electromotive force of the cell, which is 3 volts, 3.00 volt. The change in the circuit will only affect the ammeter reading, which will increase due to the decrease in total resistance, but not to the voltmeter reading. So just implication for the ammeter, but the voltmeter, there is no implication. There is no effect. Next. R is made of a resistive wire of uniform cross-sectional area 3.1 times 10 power minus 8 meter squared. Resistivity 4.9 times 10 power minus 7 ohm meter and length L. The resistance of R is given by the equations. This formula R equal KL, where K is a constant. Calculate K. Calculate the constant number. State an appropriate unit for your answer. All right, so the resistivity, this is rho. This is rho, resistivity. And area, this is A. Okay, and then the formula, is R equal KL. Also, I would like to writing another formula of R is rho times L over A. Or we can arrange this formula becomes rho over A times L. So K equal rho over A. We're going to using this formula to find K. So K equal A this one, rho this one, 4.9 10 power minus 7 over this number 3.1 times 10 power minus 8. And the result is 15.8 rounded to 16. 16 ohm meter power minus 1. What else? Number 6. Okay. We're going to continue number 6. Number 6A. State what is meant by the half-life of a radioactive nuclide. Number 6. State what is meant by the half-life of a radioactive nuclide. I have provided my explanation about this question. Half-life of a radioactive nuclide is the time required for half of nuclei in a sample of that nuclide to undergo radioactive decay. During this period, the activity or the number of decays per unit time of the sample decreases to half of its initial value. Tritium is a radioactive isotope of hydrogen. That's the tritium with hydrogen 3 and atomic number 1. The activity of a sample of tritium decreases to A0 over 8 after a time of 37.0 years. A0 is the initial activity, so this is the initial activity. Calculate the half-life of tritium. The activity decrease the activity decreases is 1 over 8 according to this information. 1 over 8 is half cube, or the activity decrease is 3 half-life. So it means the half-life of tritium equal 37.0 over 3. And this is 12.3. Deuterium and tritium undergo nuclear fusion according to this reaction equation. Identify nuclide X, right? If you look this reaction equation, that this is the deuterium, hydrogen 2, and this is the tritium, hydrogen 3. And this is the unknown nuclide, and this one, neutron. On the left side, on the left side, the atomic number on the left side is 1 from deuterium and 1 from tritium. So there are two, okay, two atomic number. Then now total mass. The total mass of deuterium, total mass, 2 of deuterium and 3 of tritium equals 5. Total atomic number is 2. Next, on the right side. On the right side, it means the total mass should be, so this is total atomic number. Two. So total mass here, it means X, it should be 5, it should be 4, because 5 minus 1 equals 4. And then number is 2, right? So it means X with the total mass 4 and atomic number 2. This is helium-4. Okay. So this is helium. Next. The following data are given for binding energies per nucleon. This data show that the energy released in this reaction is about 18 million electron volts. Energy release, energy release equal 4 times 4 times 7.074 because the total mass here 4 plus 3 minus, I mean minus, not plus, sorry, because this is on the left side and this on the right side. 3 times 2.827 minus 2 times 1.112. And if you calculate, the result is 17.6, rounded to 18. 18 million electron volts. Next. Hence, estimate the energy in joule released as a result of fusion of 1 kilogram of nuclear fuel according to this reaction. All right. It means the reaction becomes like this. I would like to add the reaction at the right side becomes x for 2 plus n plus 17.6 millions electron volts. All right. The initial, sorry, this reaction implicated for the calculation that I would like to write in 1U. 1U is atomic mass unit. One atomic mass unit is 1.661 times 10 power minus 27. And mass of mass of reactants equal 5 because total mass is 5. This is 2, this is 3, this is 4. There is 1 here of n. And then 5 times 1.5 times this number 1.661 times 10 power minus 27. So 5 is mass of deuterium and tritium. So the result is 8.3 times 10 power minus 27. And energy from 1 kg fuel equal energy release over mass of reactant. Okay, I'm gonna move here, the calculation. So it becomes 17.6 million electron volts over, this is kilograms per unit. Mass of reactants 8.3 times 10 power minus 27 kg. So we have to convert this into joule per kg because the unit in joule. If you convert into joule per kg, so 17.6 million electron volts, it should be 17.6 times 10 power 8 times 1.6 times 10 power minus 19 is minus 19, okay, over 8.3 times 10 power minus 27 kg. This is joule per kg, the unit. And if you calculate, the result is 3.39277 times 10 power 14 joule. In significant figures, 3.4, 10 power 14 joule. Next. The specific energy of typical fossil fuels is about 10 power 7 if by fossil. 10 power 7 joule per kilogram. Outline with reference to your answer in part D2, the advantage of nuclear fusion over fossil fuels as a source of energy. I have provided my explanations about this part. And the specific energy of fossil fuels is about 10 power 7. This is 10 power 7. This one, by fossil. The specific energy of nuclear fusions could be estimated at around, this is 10 power 14, according to our calculation here. One. From our previous calculation. This is 5 orders of magnitude higher than fossil fuels. The main advantage of nuclear fusions over fossil fuels is its vastly higher specific energy, of course, because this is 10 power 14 and this is 10 power 7. Number 7. In a simplified model of energy balance of the Earth, the surface of the Earth absorbs incoming solar radiations of average global intensity I0. The surface emits thermal radiations of average intensity I1. Some of the radiations emitted by the surface is absorbed by the atmosphere and re-emitted towards the surface. The average intensity of this radiation is I2. So I0 is the surface of the Earth absorbed incoming solar radiations of average. This is the global intensity. Okay. And I1 is the thermal radiation average intensity. And I2 is the average intensity of this radiation. It means I0 is I1 plus I2. Okay, the emit thermal radiation of average intensity plus the average intensity of this radiation. Okay, like this. So I1 towards to upwards and I 2 to downwards, I0 as well, downwards. So I1 is I2, okay, plus I1 is I2 plus I0. Okay, we are going to calculate this. All right. So I1 equal I0 plus I2. I have to, based on this diagram, wait, based on this diagram that I1, I0 plus I2. Okay. Next, explain the effect of an increase in the concentrations of greenhouse gases, GHG, in the atmosphere on I2. I have provided my solution, my explanation about this, my opinion, that with an increase in greenhouse gases, the atmosphere becomes more effective at trapping thermal radiation. This causes an increase in the intensity of, this is I2 actually, of I2. It's I2. The radiation that is absorbed by atmosphere and re-emitted towards the Earth's surface. This leads to an overall warming of the Earth's surface because the energy that would have been lost to space is instead radiated back to the surface, enhancing the greenhouse effect. This is my explanations about this question. Next, the following data are given. Now, I0 this one, I2 this one, as I written on upwards that I1 equal I0 plus I2 based on the diagram. Determine the average temperature of the surface of the Earth according to this model, right? It means I1 equal to 40 plus 150. It is 390. Okay. And then according to the Stefan Boltzmann law that uh, I1 equal sigma times T power 4, which T is temperature. And sigma is Stefan Boltzmann number, 5.67 times 10 power minus 8. So it means T power 4 is I1 over sigma, or T equal I1 over sigma power 1 over 4. So T equal I1 is 390 over Stefan Boltzmann number is 5.67 times 10 power minus 8. It is 288 Kelvin. The unit is the unit temperature Kelvin. You may calculate this. You may make sure. Number 8, a distance r from the center of a planet. The gravitational potential due to the planet is Vg, and the gravitational field strength is G. So that Vg equal minus Gr. Okay. I will start with the relationship between gravitational potential, Vg, and gravitational field strength, G. The gravitational field strength, G, is a negative gradient of the gravitational field potential, or Vg. So I would like to write in Vg equal, or sorry, G equal, okay, G equal minus dVg dr. Okay, so the gravitational field strength is negative gradient of the gravitational field potential, Vg. For planet with a mass m, the gravitational potential at a distance r is given by if the mass m Vg equal minus g times m equal minus gm over r. So I can writing that Vg equal minus gm times r power minus 1. Now, differentiate Vg with respect to r will be, sorry, dVg, dVg dr respect to r is equal minus 1 times minus 1, positive 1, gm r minus 2. Or I can writing dVg dr equal gm over r squared. This is m. And then it give us the gravitational field strength that G, because this is dVg dr, G equal minus dVg dr equal gm over r squared. So because G equal minus dVg dr. And the relationship between G and Vg, is confirmed. So to find Vg in terms of G, we can rearrange that G equal, I'm going to continue here, G equal Gm over R squared, and Vg equal minus Gm over this one, over R, this one. And now GR, or this one derived becomes GR squared equal GM. Like that. This is M. So now substitute GM equal GR squared into this equation. So it becomes PG equal minus GR squared over R. Again, because GM equal GR squared. So Vg equal minus GR, because R divided by R. Prove this one. A satellite of mass 750 kilograms orbits the Earth in a circular orbit of radius 1.0 times 10 power 7 meters. Calculate the magnitude of the gravitational field strength at the orbital radius of satellite. Okay. So radius is 1.0 times 10 power 7 meters. And Vg is minus 4 times, why minus 4? Because Well, if 1, the radius 1, Vg is here, Vg is this one, minus 4. Minus 4 times 10 power 7. Again, if r equal 1.0 times 10 power 7, the Vg is minus 4 times 10 power 7. That's why here, minus 4 times 10 power 7 joule per kg. Next, so it means the gravitational field strength G equal minus Vg over R. And it is minus of minus 4. It means positive 4. 10 power 7 over 1.0 times this one, 10 power 7. So it is 4.0 meter per second squared. The gravitational force acting on the satellite. We are going to use this formula F equal m times g. M is 750, and then g is 4. G is 1, 4, and this mass 750. So force equal, this is Newton over kg, this is 4 kg. 4 4 kg. So the result is 3,000 Newton, or 3 times 10 cube newtons. The satellite is moved to a new circular orbit. The orbital radius of the satellite increases by 2 kilometers. Outline why the magnitude of the gravitational field strength at the new orbit is approximately the same as the old orbit. Okay, see part 1, because if we compare with the original radius, I haven't yet typing my explanation, so I have to writing here, because if we compare with the original radius, the change in the orbital radius is very small. Okay, this is my explanation. See part 2. Determine the change in the total orbital energy of the satellite. Right. So I'm going to using this formula that potential energy, the change in potential energy equal m times g times the change on radius. It's going to be 750 times 4.0 times 2.0 times 10 cube joule. And the result is 6,000 times 10 cube. Okay, 10 cube joule, or 6,000 times 10 power 6, 10 power 6 joule. And the next step is change energy. The total energy is half times change of potential energy. It means half times 6 times 10 power 6 joule. And the result is 3 times 6 power 6 joule. That's the solution. Number 9, an object attached to a spring oscillates with simple harmonic motion in a horizontal plane. The graph shows how the kinetic energy of the object varies with the displacement x. This is the graph. Uh, this is the energy axis, and this is the displacement axis. State the amplitude of the motion. The amplitude of the motion is the displacement. So to the left is 6 and to the right also 6. So the answer is 6 centimeters. Draw on the axis above the variations with x of the potential energy stored in the spring. Okay, so uh, this is this this is the graph of kinetic energy, and the potential energy I'm going to sketch like this. Okay, and then all right. Okay, so this is, I forgot, this is a potential energy graph. Explain how many times during one oscillation, the kinetic energy of the object and the potential energy stored in the spring are equal. Okay. Uh, if you look this, if you look this graph, that per half oscillation, this is half oscillation. One oscillation is happening if one wave, at least one wave. So this is only half waves. It means this is one. This is half oscillations. In half oscillation between kinetic energy and potential energy. So actually, this is kinetic energy equal potential energy. Okay. Okay, this is the kinetic energy maximum and this is potential energy maximum. So in half oscillation, it has it has 2 points. Okay, one, two. It has 2 points. It means I'm going to write it here. Uh, per half oscillation, it has 2 points. Okay, it means uh, during one half oscillations it has 2 points. It means during one oscillation, it has 4 points. So it means how many times during one oscillation? 4 times. Yeah, the solution is 4 times. That's the intersection. The mass of the object is 0.15 kg. This is the mass. Show that the period of the oscillations is about 0.7 seconds. I would like to start with total energy. Total energy is half times m omega squared, and displacement. A is displacement squared. So it means total energy half times mass is 0.15, and this is, yeah, we are going to find omega squared, and this is A is displacement is 6 centimeters becomes, let me check. Yeah, 6 centimeters. I forgot just now. 6 centimeters. So it means omega equals square root uh, 2 times, wait, square root of 2 times total energy over m times a squared, or the root of 2 times total total energy is, wait, 20, just now 20 times 10 power, this one, 20 total energy, this one. Okay, the total energy is 20. 2 times 20 times 10 power minus 3, because millijoule, mc millijoule is 1 over 1000 kilojoule, and then 20 times this is 20 times 20 millijoule, 20 times 10 power minus 3 joule. Okay, so it's gonna be m is 0.15, and displacement is 0.06. So 6 centimeters comes 0.06 meters. Maybe if you calculate, I already calculate this number. The result is 8.6066, rounded to 8.6 radian per second. Now we're going to find the period. Period is T. T equal to pi over 3.6, 2 pi over omega, I mean, right? 2 pi over omega. It means 2 times 3.14 over 1, 6.8.6. And the result is 0.72967, rounded to 0.7 seconds. So, proof. Calculate the maximum force exerted on the object by the spring. I would like to find the maximum acceleration. The maximum acceleration is 0.060. Okay. Is their displacement times omega. So actually the formula, I would like to writing the formula actually. Supposed to be I have to writing the formula. The formula is omega times displacement squared. So omega is 8.6 times 0.060 squared. I sorry. Supposed to be this is omega squared. Omega squared. Okay. And if you calculate, the result will be 4.444, rounded to 4.44 meter per second squared. And after that, this one, maximum force. Maximum force, we can gain through the formula m, or mass times acceleration maximum. So mass is 0.15 times 4.44, and the result is 0.67 Newton. A 1.0 millifarad capacitor is connected in series to a 2.3 kilo ohms resistor and a cell of negligible internal resistance. This is the circuit. The capacitor is initially unchanged at time t equals 0. The switch is moved to position A. The initial current in the resistor is 3.9 milliamps. Calculate the EMF of the cell. EMF symbol is epsilon. So we are going to calculate, we are going to find the EMF. Okay. On this problem, these questions, we have information regarding the initial currents. Okay, initial current is 3.9 0.9 milliamps. I would like to convert into 3.9 times 10 power minus 3 amps. And after that, resistor is, right? Resistor is 2.3 kilo ohms. So R equal 3 2.3 kilo ohms. It means 3 times 10 cube ohms. And then epsilon or EMF equal initial current times resistor plus VC. What is VC? VC is potential difference across the capacitor. Okay, so epsilon equal and VC equals 0. Okay, and then epsilon equal 3.9 times 10 power minus 3 amps times R 2.3 times 10 cube ohms plus 0. And if you calculate, the result is 8.97 rounded to 9 volts. Explain why the current in the resistor decreases with time. I have provided my solution, my explanation. This one. The current decreases over time because the capacitor gradually takes on more charge, causing its potential difference or voltage to increase and thereby reducing the voltage across the resistor, which in turn decreases the current. Next, at time t equal 5 seconds, the switch is moved to position B. Draw on the circuit diagram above an arrow showing the direction of the conventional current in the resistor for t greater than 5.0 second. Okay. Uh, when the when when t greater than 5.0 second, after the switch move to position B, the switch move to position B, it means to move the switch move here. I'm going to clean this switch to A. Okay. Okay, the circuit becomes like this. Okay. For t greater than 5.0 second, after the switch is moved to position B, the current will flow. Actually, the current will flow from the positive terminal of the capacitor. This is the capacitor through the resistor to the negative terminal of the capacitor, right? Through the resistor. So it means the direction arrows to upward like this. Because the electricity flows through the capacitor and then resistor, after that resistor. Okay, I think that is clear. Next, the graph shows how the voltage across the capacitor varies with T. This is the graph. Estimate the energy dissipated in the resistor between T 5 second and T 8 second. Right. I would like to using the formula EC. EC is energy stored in capacitor. EC equal half CV squared. Right. So it means AC equal C is 1.0 times 10 power minus power minus 3. So half times 1.0 times 10 power minus 3. And and then phi or voltage or potential difference when t equal 5, the voltage or potential difference 8, and when t equal so energy dissipated occur during this interval 5 to 8, right? When t equal 8, the voltage or potential difference is this one, 2.2. So 8.0 squared minus 2.2 squared. And if you calculate half times 1, half times 10 power minus 3 times is 64.0 minus 2.2 times 2.2 is 4.84. And the next calculation will be, this is half times, I have calculated this, is 29.58 times 10 power minus 3. And we have to convert becomes the significant figures 2.958 times 10 power minus 2 joule, rounded to 3, times 10 power minus 2 joule. Next, a rectification circuit contains a diode bridge, an alternating current AC supply, and a load resistor R. A capacitor C is added in parallel with the resistor. This is the capacitor added to uh, resistor, okay, as the parallel. This is the parallel circuit, right? State and explain the effect of the capacitor on the current in R. I have provided my explanation also. This capacitor stores charge. When a capacitor C is added in parallel with the load resistor R, it helps smooth out the voltage and affects the current in the resistor. When potential difference across R increases, the capacitor is being charged. When potential difference or voltage decreases between charging cycles, the charge is released through R and the diodes prevent the capacitor from discharging through the AC source. AC is alternating current source, electricity source. Number 11. In experiment to investigate the photoelectric effect, a beam of monochromatic light is incident on a metal surface. When the frequency of light is less than a certain threshold frequency F0, no electrons are emitted from the surface. Outline how this observation supports the photon model of light. I have provided my explanations about this question. According to the photon model, light is quantized and consists of particles called photons. each with an energy E equal H times F. The photon model suggests that the energy of photon depends directly on the frequency of the light. When F less than F0, photon energy is less than the work function energy needed to release an electron from the metal surface. You may add with your words or you may add with your sentence about this explanation. The collecting plate of the photoelectric cell is at a variable potential phi relative to the metal surface. This is the diagram. The graph shows the variations of the current I in the ammeter with phi for light of wavelength. This is the graph. Okay, the graph is going from the right side to the left side and downwards and stop here. Explain why I is 0 for large negative p. I have provided as well for this question, my explanation. When the collecting plate is at a large negative potential, it creates an electric field that repels the emitted electrons. The maximum kinetic energy of the emitted electrons is determined by the energy of the photons and the work functions of the metal. If the potential phi becomes sufficiently negative, it will create an opposing electric field strong enough to stop even the fastest electrons from reaching the collecting plate. For light of wavelength 430 nanometers, the emitted electrons have enough energy to reach the collecting plate under normal conditions. You may add your opinion, you may add your sentences, you may add your words into these explanations according to your opinion. Next, approaches. A constant value for large positive phi. I have provided also my explanations about this. For large positive potential difference phi, the current approaches a constant value because the electric field is strong enough to attract all the emitted electrons, ensuring that every electron emitted from the metal reaches the collecting plate. At this point, the current is limited by the rate of electron emission and the intensity of the light, and further increasing the potential does not increase the current, leading to a saturation value. Also, you may add your opinion, your sentences, or your words into this explanation based on your analysis. Next, calculate in electron volts the energy of a photon of wavelength 430 nanometers. Right. I would like to using the formula E equal hc over lambda. This is lambda. E is energy of the photon. H is Planck constant number. C is speed of light. Lambda is wavelength of light. According to this information, wavelength of light is 430 nanometers. Right. Let's we substitute dash numbers. H is Planck's constant number, 6.626 times 10 power minus 34. The unit is joule second times, this is the speed of light, 3.0 times 10 power 8. And the unit is meter per second. Over lambda is 430 nanometers. I would like to convert into 430 times 10 power minus 9 meters. So over 430 times 10 power minus 9. Okay, minus 9. And if you calculate, sorry, I have to make sure this is 9. Okay, minus 9. If you calculate, I have calculated this, and the result is 4.63 times 10 power minus 19 joule. Now, the questions need the unit is electron volts. So we have to convert this number from joule into electron volt. As you know that one electron volt, if we convert into joule, is 1.602 times 10 power minus 19 joule. This is 1 electron volt. So how we convert it? We have to divide by this number. So E equal 4.63 times 10 power minus 19 joule over this number 1.602 times 10 power minus 19 joule over electron volt. And the result is 2.89 electron volt, or in significant figures, 2.9 electron volt. I think clear. This one, the work functions of the metal surface. To solving these questions, I would like to using the photoelectric effect theory. The photoelectric effect theory is described by an equation, and the equation is E photon equal V plus E kinetic. So E photon is energy of the incident photon. V is the work function. E kinetic is the kinetic energy of the emitted electron. So the question is work function. So it means we are going to find work function V. V equal E photon minus E kinetic. Energy photon minus energy kinetic. Now, the energy kinetic is equal. If you look the graph, you may evaluate the graph that the graph stop at 0.9. Okay, this is the last stop of the movement of the graph. So phi equal, this is 2.9, a phi minus 0.9 a phi. and the result is two electron volt.